All right, let's look at some rational functions and what we might use them for in applications. So this is an introduction to what we'll call rational functions, and I'll define that in a minute. But let's look at this function here, capital C. C is the ratio of 80,000 times P over the difference 100 minus P. And we're told that a utility company burns coal to generate electricity, and the cost C in dollars of removing P% of the smokestack pollutants is given by our formula here. So P is a percent and C is cost in dollars. And since P is a percent, we've got a restricted domain. P is between 0 and 100, and we don't expect to extract 100% of pollutants. Now let's say we are a member of the state legislature and we're considering a law that would require the utility company to remove 90% of the pollutants from their smokestack emissions. The current law requires 85% removal. How much additional cost would the utility company incur as a result of our new law? Ooh, I like this example. Okay, so we would like to know the new cost, removing 90% of the pollutants, and how much more that cost would be than removing 85% of the pollutants. Okay, so currently the requiring 85% removal. We're going to plug in 85 wherever there used to be a P, and the cost is the product 80,000 times 85 over the difference 100 minus 85, and so we'll have the product divided by 15, and you can double check that. That's almost $500,000. $453,000, 333 approximation. Now when we do that calculation and see what the cost is when we implement the new law, and we plug in the 90% for P, that's our input, and now we have this new product divided by the difference 100 minus 90. So we have the new product divided by 10, and that's 72. What is that? Almost $750,000, 720,000. So we're going to compare. The new cost of extracting pollutants is more. How much more? 720,000 minus 453,333, and so that difference is about $267,000. Like that. An application of using a rational function. Okay, so a rational function is a quotient of two polynomial functions. So we'll assume the numerator is a polynomial function, maybe of degree n, and the denominator is a polynomial function, maybe of degree m. They don't have to be the same degree. But what we do have to restrict, the denominator cannot be the zero polynomial. It can be any other polynomial. And we know from previous chapters that the domain of an algebraic expression is a set of values. It's a set of all real numbers for which the expression is defined. And so we want to make sure we don't divide by 0 or take the square root of a negative number, because we wouldn't get a real output, things like that. Now for these kind of expressions, the domain is really just the real numbers that don't make the denominator 0. So we would include all real numbers except any x value that made the denominator 0. So let's use this definition and find some domains. Okay, so the simplest rational function we could create would be 1 over x. The numerator is a constant polynomial, so it would have degree 0. The denominator is a linear polynomial and would have degree understood 1. And we wouldn't want x to be 0, so we would have exclude 0 from the domain. But x could be any other real number. We call this the reciprocal function, and we'll look at this in other examples. Now typically we'll have something a little more complicated. So I have a degree 2 polynomial over a different degree 2 polynomial, and I need to know when that denominator would be 0. Okay, so to determine the domain, we would factor that denominator. And I can find the factors of -4 that add up to 3, 4, and -1. So the quadratic factors into these two linear factors. Now when is x plus 4 equal to 0? Exactly when x is -4. When is x minus 1 equal to 0? exactly when x is 1. So these two values, -4 and 1, have to be excluded from the domain. And the domain is the set of all reals except those two values. Okay. Now some things we're going to have to watch out for. Sometimes these functions can be simplified, and we're tempted to simplify, but we don't want to change the domain. So maybe double check my factorization here. Yeah, those both look pretty good. And look, this product has a factor of x plus 2, as does the denominator have a factor of x plus 2. So we've been told that anything divided by itself is 1. Well, you have to be a little more careful. You don't want to have 0 over 0. When would x plus 2 be 0? When x is -2. So we can cancel with those red lines and rewrite our original function f as this more simple ratio, but we have to tell the reader that x cannot be -2 because we could not plug in -2 to the original. Okay, that means there's going to be a hole in the graph at -2. And just for later, we'll talk about vertical asymptotes. There would only be 1 for this function. The denominator would be 0 at 3, so 3 is a vertical asymptote. But this place where the function is undefined would not be a vertical asymptote. That would be a removable discontinuity or a hole in the graph. But the domain of the original function f is all real numbers except 3 and -2. Everywhere the function's undefined. Okay, you want to maybe stop the video and see if you can factor both the numerator and the denominator and see if this function will simplify. Okay, yeah, the numerator is a difference of two perfect squares, and so does factor. And with a little guess and check, we find that the denominator also factors. And yeah, there's this common factor of x minus 1. And when we're tempted, and we can cancel x minus 1, over x minus 1, but we have to tell the reader that x can never be 1. So this simplified ratio looks like it's defined at 1, but our original function is not. So what would be the domain of the original expression? There would be two values we'd exclude, not just 1, but -1/2. Okay. And a little preview for later. We're going to be looking for different kinds of asymptotic behavior. And so I've shown in this example just kind of this really neat graph. H of x is graphed here in the green. So h of x was a degree 2 over a degree 1 polynomial. And a person could do long division. And so the dividend divided by the divisor results in a quotient of 2x minus 1 and a remainder of -3. If you want to look down here, you can review that. Okay, so h of x is not quite linear because it has this remainder. But for large values of x, this remainder becomes negligible, and for large values of x, h behaves like the line 2x minus 1. So in blue, I've tried to graph a line with intercept -1 and slope 2. And then that green curve approaches the imaginary blue line for large values of x. Okay. Now function h could not simplify, and function h is undefined at -2. Moreover, at -2 we have a vertical asymptote that I've represented as an imaginary red line. You might want to see if you can graph that on your graphing calculator just as an introduction, and make sure you put grouping symbols around the polynomial in the numerator and a polynomial in the denominator.